Okay, so we introduced a toy model. Let's just think about it a bit. So let's think about the phase transition of ice melting. So if you think about ice, well, all of the atoms are in a very regular pattern. So they're just sitting there. They might be vibrating a little bit, but there's not too much energy. So this would be like the state E naught. Um, on the other hand, if you warm this up a bit so that you get water, the water particles will be able to move around. They've got kinetic energy. They shift their positions. So because each of these water particles is moving around with some energy, you expect it to be at a higher energy. So that's the E1. It's at a higher energy. Now let's think about the degeneracy of these states. If you think about the number of states associated to the ice, well, you've got these atoms. They don't move very much. They're in this regular atom. Maybe they vibrate a little bit, but there's not too many states. On the other hand, if you think about the water, well, these particles can move around a lot. They can have velocities. The velocities can vary. The direction in which the particle is moving can vary. The position of the particle in water, the water atoms are not fixed somewhere. They move around. So there's an enormous number of states. And that's what this model is mimicking. One state at low energy versus very, very many states at a higher energy. And we're saying that this competition is between energy, and really at this stage, it looks like it's a competition between energy and degeneracy because it's N that played a role at very high temperatures. Now I just want to tighten this up a bit and to show you that this really is a competition between energy and entropy. So what is entropy? Well, we have a macro state. So this macro state, we know something about the state, but we certainly haven't measured enough to know all of the details about the state. And because of that, there are many microstates that correspond to the single macro state. So let's say many microstates. And then the entropy would be a property of this macro state. So what would the entropy of the macro state be? So I've called this S macro. This would be a log of the number of microstates. So it would really be like a log of the degeneracy. So in our previous model, well, the label for the macro state was the energy, the E naught and the E1. And then the energy would have been the log of the degeneracy. Okay, so now I want to think about the partition function. And the partition function is a sum over I, the sum over the states, times by pi, the probability for each state. And typically what happens in statistical mechanics is that there's a specific state that dominates the sum. And that's the state you'll find the system in. So let's see how that happens. So, if we want to do the sum, what would it be? Will it be a sum over I? Okay. And let's say that we're summing e to the minus beta ei. And ei are the energies of the macro states. So we'd better multiply by ni, which tells us how many microstates correspond to that given macro state. So it's the degeneracy. How many states have the energy of ei? And we can write this as sum over I, e to the minus beta ei plus log of ni. So that's just trivial. I've just lifted the ni into the exponent. Now I want you to remember that beta is equal to 1 over t. So of course, obviously that means that beta times t is equal to 1. And I'm going to be using this in a minute. So I want to rewrite this as a sum over I, e to the minus beta. I'll have beta outside. I'll have an ei. Because I've pulled out a minus, I've got a minus sign here. And now I'm going to use this condition that beta times t is 1. So I'm going to put a t there, so the beta times t is 1. And then I've got a log of ni. So what you see is, if we want to see which term dominates the sum, it's not the energy we should minimize. The quantity we should minimize for each state, so Fi, it's given by Ei minus T times by the log of Ni. And this is called the Helmholtz free energy. The Helmholtz free energy. And identifying the log of Ni as the entropy, this is just given by the energy of the state minus T times the entropy of the state. And it's the Helmholtz free energy that we minimize to figure out which state actually dominates the sum in the partition function, and that tells us which state we'll find the system in. So if we're at very small temperatures, so at very, very small T, you can see that the Helmholtz free energy is approximately E, and we should minimize the energy. Okay? So this is what we get at low temperatures. Now, at very big temperatures, then the Helmholtz free energy, well, now I can forget the first term, so it's just minus T times by SI. We want to minimize the Helmholtz free energy. Because of that minus sign, it means we want to maximize the entropy. And for any equilibrium phase transition, the phase transition is driven by this competition of minimizing the energy and maximizing the entropy. So at small t, you minimize the entropy. Sorry, you minimize the energy. At very big T, you maximize the entropy. And there's some point in between where it's not clear who wins the competition. And these two effects compete with each other. And this is where we have the phase transition. So we have a phase transition when the energy entropy competition is matched. I mean, when we're swapping from energy dominating to entropy dominating. So when the two effects just match each other, that's when we have the phase transition. And it's that phase transition that is related to the CFT. Actually, what's related to the CFT is actually what's called a continuous phase transition. So when you've got a continuous phase transition, this is what is described by a CFT. So continuous phase transitions are what's relevant for CFT. And I now want to describe what a continuous phase transition is. And a very nice system to describe this in is the Ising spin magnet. So let's describe this now, and this will illustrate what we want to describe very clearly. So what do? Well, we have a lattice, so we've got a whole bunch of dots. I'm drawing these all in a line, but that's not the only thing you could consider. You could have had the dots lying on a plane. You could have had the dots in a volume in higher dimensions, whatever. I'm putting them on a line, but you could have considered things that were more interesting. And what these spins can do, they can point either spin up or they can point down. So I'm just going to give these spins some values. When it points up, we've got +1. When it points down, we have got -1. So I want to invent a Hamiltonian. So I'll call my Hamiltonian H. There'll be some scale, some coupling that sets the strength of the Hamiltonian. Let's call that coupling G. And then what the energy is, I'm going to take a sum and I'm going to take the spin at site I. So I is a site label. Okay. So what does that mean? Well, this dot over here could have been I is equal to 1. This dot is I is equal to 2, 3, 4, 5. So this dot could have been I is equal to 5. So changing the value of I changes which site you're looking at. And this energy is from spins interacting at different sites. So we'll have SI times by SJ. Now, neighboring spins will have a big effect because these spins are very close to each other. So this spin, the second spin that I've just ringed in blue, it'll interact strongly with the two spins in next to it, but much less strongly with spins that are more distant from it. So the way that we typically model that is we say that when we do the sum, we only sum over nearest neighbors, and we denote this as ij. And that means I only take spin I with the spin to the left and the spin to the right. And then what do I want to do? I want the energy to be lowered when the spins align, because I want the spins to energetically align. Now, if two spins point in the same direction, it's a plus one times a plus one, which is one, or a minus one times a minus one, which is one. If spins point in opposite directions, it's a plus 1 times a minus 1, which is a minus 1. So to get the spins to align, I should actually include a minus sign in the Hamiltonian. So this minus sign is included, so it is energetically favorable to align spins. So that's why we need that minus sign. Good. Okay, we are going to keep going in a minute.